Chapter 2 of Gardening Without Irrigation, or Without Much, anyway. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Betsy Bush, August 2009. Gardening Without Irrigation, or Without Much, anyway, by Steve Solomon. Chapter 2 Water-Wise Gardening Science. Plants are water. Like all other carbon-based life forms on Earth, plants conduct their chemical processes in a water solution. Every substance that plants transport is dissolved in water. When insoluble starches and oils are required for plant energy, enzymes change them back into water-soluble sugars for movement to other locations. Even cellulose and lignin, insoluble structural materials that plants cannot convert back into soluble materials, are made from molecules that once were in solution. Water is so essential that when a plant can no longer absorb as much water as it is losing, it wilts in self-defense. The drooping leaves transpire, evaporate, less moisture because the sun glances off them. Some weeds can wilt temporarily and resume vigorous growth as soon as their water balance is restored. But most vegetable species aren't as tough. Moisture-stressed vegetables may survive, but once stressed, the quality of their yield usually drops markedly. Yet in deep open soil west of the Cascades, most vegetable species may be grown quite successfully with very little or no supplementary irrigation and without mulching, because they're capable of being supplied entirely by water already stored in the soil. Soil's water-holding capacity. Soil is capable of holding on to quite a bit of water, mostly by adhesion. For example, I'm sure that at one time or another you have picked up a wet stone from a river or by the sea. A thin film of water clings to its surface. This is adhesion. The more surface area there is, the greater the amount of moisture that can be held by adhesion. If we crushed that stone into dust, we would greatly increase the amount of water that could adhere to the original material. Clay particles, it should be noted, are so small that clay's ability to hold water is not as great as its mathematically computed surface area would indicate. Surface area of 1 gram of soil particles. Particle type, very coarse sand. Diameter of particles in millimeters, 2.00 to 1.00. Number of particles per gram, 90. Surface area in square feet centimeters, 11. Particle type, coarse sand. Diameter of particles, 1.00 to 0.50. Number of particles, 720. Surface area, 23. Particle type, medium sand. Diameter of particles, 0.50 to 0.25. Number of particles, 5,700. Surface area, 45. Particle type, fine sand. Diameter of particles, 0.25 to 0.10. Number of particles, 46,000. Surface area, 91. Particle type, very fine sand. Diameter of particles, 0.10 to 0.05. Number of particles, 772,000. Surface area, 227. Particle type, silt. Diameter of particles, 0.05 to 0.002. Number of particles, 5,776,000. Surface area, 454. Particle type, clay. Diameter of particles, below 0.002. Number of particles, 90,260,853,000. Surface area, 8 billion. Source: Foth, Henry D. Fundamentals of Soil Science, 8th edition, New York, John Wiley & Sons, 1990. This direct relationship between particle size, surface area, and water holding capacity is so essential to understanding plant growth that the surface areas presented by various sizes of soil particles have been calculated. Soils are not composed of a single size of particle. If the mix is primarily sand, we call it a sandy soil. If the mix is primarily clay, we call it a clay soil. If the soil is a relatively equal mix of all three, containing no more than 35% clay, we call it a loam. Available moisture, inches of water per foot of soil. Soil texture, very coarse sand. Average amount, 0.5. Coarse sand, 0.7. Sandy, 1.0. Sandy loam, 1.4. Loam, 2.0. Clay loam, 2.3. Silty clay, 2.5. Clay, 2.7. Source: Fundamentals of Soil Science. Adhering water films can vary greatly in thickness, but if the water molecules adhering to a soil particle become too thick, the force of adhesion becomes too weak to resist the force of gravity, and some water flows deeper into the soil. When water films are relatively thick, the soil feels wet and plant roots can easily absorb moisture. Field capacity is the term describing soil particles holding all the water they can against the force of gravity. At the other extreme, the thinner the water films become, the more tightly they adhere and the drier the earth feels. At some degree of desiccation, roots are no longer forceful enough to draw on soil moisture as fast as the plants are transpiring. This condition is called the wilting point. The term available moisture refers to the difference between field capacity and the amount of moisture left after the plants have died. Clayey soil can provide plants with 3 times as much available water as sand, 6 times as much as a very coarse sandy soil. It might seem logical to conclude that a clayey garden would be the most drought resistant, but there's more to it. For some crops, deep sandy loam can provide just about as much useful moisture as clays. Sandy soils usually allow more extensive root development, so a plant with a naturally aggressive and deep root system may be able to occupy a much larger volume of sandy loam, ultimately coming up with more moisture than it could obtain from a heavy, airless clay. The sandy loams often have a clayey, moisture-rich subsoil. Because of this interplay of factors, how much available water your own unique garden soil is actually capable of providing and how much you will have to supplement it with irrigation can only be discovered by trial. How soil loses water. Suppose we tilled a plot about April 1st and then measured soil moisture loss until October. Because plants growing around the edge might extend roots into our test plot and extract moisture, we'll make our tilled area 50 feet by 50 feet and make all our measurements in the center. And let's locate this imaginary plot in full sun on flat, uniform soil. And let's plant absolutely nothing in this bare earth. And all season, let's rigorously hoe out every weed while it is still very tiny. Let's also suppose it's been a typical maritime northwest rainy winter, so on April 1 the soil is at field capacity, holding all the moisture it can. From early April until well into September, the hot sun will beat down on this bare plot. Our summer rains generally come in insignificant installments and do not penetrate deeply. All of the rain quickly evaporates from the surface few inches without recharging deeper layers. Most readers would reason that a soil moisture measurement taken 6 inches down on September 1st should show very little water left. 1 foot down seems like it should be just as dry, and in fact most gardeners would expect that there would be very little water found in the soil until we got down quite a few feet, if there were several feet of soil. But this is not what happens. The hot sun does dry out the surface inches, but if we dig down 6 inches or so, there will be almost as much water present in September as there was in April. Bare earth does not lose much water at all. Once a thin surface layer is completely desiccated, be it loose or compacted, virtually no further loss of moisture can occur. The only soils that continue to dry out when bare are certain kinds of very heavy clays that form deep cracks. These ever-deepening openings allow atmospheric air to freely evaporate additional moisture. But if the cracks are filled with dust by surface cultivation, even this soil type ceases to lose water. Soil functions as our bank account, holding available water in storage. In our climate, soil is inevitably charged to capacity by winter rains, but then all summer growing plants make heavy withdrawals. But hot sun and wind working directly on soil don't remove much water. That is caused by hot sun and wind working on plant leaves, making them transpire moisture drawn from the earth through their root systems. Plants desiccate soil to the ultimate depth and lateral extent of their rooting ability, and then some. The size of vegetable root systems is greater than most gardeners would think. The amount of moisture potentially available to sustain vegetable growth is also greater than most gardeners think. Rain and irrigation are not the only ways to replace soil moisture. If the soil body is deep, water will gradually come up from below the root zone by capillarity. Capillarity works by the very same force of adhesion that makes moisture stick to a soil particle. A column of water in a vertical tube, like a thin straw, adheres to the tube's inner surfaces. This adhesion tends to lift the edges of the column of water. As the tube's diameter becomes smaller, the amount of lift becomes greater. Soil particles form interconnected pores that allow an inefficient capillary flow, recharging dry soil above. However, the drier soil becomes, the less effective capillary flow becomes. This is why a thoroughly desiccated surface layer only a few inches thick acts as a powerful mulch. Industrial farming and modern gardening tend to discount the replacement of surface moisture by capillarity, considering this flow an insignificant factor compared with the moisture needs of crops, but conventional agriculture focuses on maximized yields through high plant densities. Capillarity is too slow to support dense crop stands where numerous root systems are competing, but when a single plant can, without any competition, occupy a large enough area, moisture replacement by capillarity becomes significant. How plants obtain water. Most gardeners know that plants acquire water and minerals through their root systems, and leave it at that. But the process is not quite that simple. The actively growing tender root tips and almost microscopic root hairs close to the tip absorb most of the plant's moisture as they occupy new territory. As the root continues to extend, parts behind the tip cease to be effective because, as soil particles in direct contact with these tips and hairs dry out, the older roots thicken and develop a bark, while most of the absorbent hairs slough off. This rotation from being actively foraging tissue to becoming more passive conductive and supportive tissue is probably a survival adaptation because the slow capillary movement of soil moisture fails to replace what the plant used as fast as the plant might like. The plant is far better off to aggressively seek new water in unoccupied soil than to wait for the soil its roots already occupy to be recharged. A simple bit of old research magnificently illustrated the significance of this. A scientist named Dittmer observed in 1937 that a single potted ryegrass plant allocated only 1 cubic foot of soil to grow in made about 3 miles of new roots and root hairs every day. Ryegrasses are known to make more roots than most plants. I calculate that a cubic foot of silty soil offers about 30,000 square feet of surface area to plant roots. If 3 miles of microscopic root tips and hairs, roughly 16,000 lineal feet, draws water only from a few millimeters of surrounding soil, then that single rye plant should be able to continue ramifying into a cubic foot of silty soil and find enough water for quite a few days before wilting. These arithmetical estimates agree with my observations in the garden and with my experiences raising transplants in pots. Lowered plant density, the key to water-wise gardening. I always think my latest try at writing a near-perfect garden book is quite a bit better than the last. Growing vegetables west of the Cascades recommended somewhat wider spacings on raised beds than I did in 1980 because I'd repeatedly noticed that once a leaf canopy forms, plant growth slows markedly. Adding a little more fertilizer helps after plants bump, but still the rate of growth never equals that of younger plants. For years I assumed crowded plants stopped producing as much because competition developed for light. But now I see that unseen competition for root room also slows them down. Even if moisture is regularly recharged by irrigation, and although nutrients are replaced, once a bit of earth has been occupied by the roots of one plant, it is not so readily available to the roots of another. So allocating more elbow room allows vegetables to get larger and yield longer and allows the gardener to reduce the frequency of irrigations. Though hot baking sun and wind can desiccate the few inches of surface soil, withdrawals of moisture from greater depths are made by growing plants transpiring moisture through their leaf surfaces. The amount of water a growing crop will transpire is determined first by the nature of the species itself, then by the amount of leaf exposed to sun, air temperature, humidity, and wind. In these respects, the crop is like an automobile radiator. With cars, the more metal surfaces, the colder the ambient air, and the higher the wind speed, the better the radiator can cool. In the garden, the more leaf surfaces, the faster, warmer, and drier the wind, and the brighter the sunlight, the more water is lost through transpiration. Dealing with a surprise water shortage. Suppose you are growing a conventional, irrigated garden and something unanticipated interrupts your ability to water. Perhaps you are homesteading and your well begins to dry up. Perhaps you're a backyard gardener and the municipality temporarily restricts usage. What to do? First, if at all possible before the restrictions take effect, water very heavily and long to ensure there is maximum subsoil moisture. Then eliminate all newly started interplantings and ruthlessly hoe out at least 75% of the remaining immature plants and about half of those about 2 weeks away from harvest. For example, suppose you've got a 4-foot wide intensive bed holding 7 rows of broccoli on 12-inch centers, or about 21 plants. Remove at least every other row and every other plant in the 3 or 4 remaining rows. Try to bring plant density down to those described in Chapter 5, How to Grow It A to Z. Then shallowly hoe the soil every day or two to encourage the surface inches to dry out and form a dust mulch. You water-wise person, you're already dry gardening. Now start fertigating. How long available soil water will sustain a crop is determined by how many plants are drawing on the reserve, how extensively their root systems develop, and how many leaves are transpiring the moisture. If there are no plants, most of the water will stay unused in the barren soil through the entire growing season. If a crop canopy is established midway through the growing season, the rate of water loss will approximate that listed in the table in Chapter 1, Estimated Irrigation Requirement. If by very close planting, the crop canopy is established as early as possible and maintained by successive interplantings, as is recommended by most advocates of raised bed gardening, water losses will greatly exceed this rate. Many vegetable species become mildly stressed when soil moisture has dropped about half the way from capacity to the wilting point. On very closely planted beds, a crop can get in serious trouble without irrigation in a matter of days. But if that same crop were planted less densely, it might grow a few weeks without irrigation, and if that crop were planted even farther apart so that no crop canopy ever developed and a considerable amount of bare, dry earth were showing, this apparent waste of growing space would result in an even slower rate of soil moisture depletion. On deep open soil, the crop might yield a respectable amount without needing any irrigation at all. West of the Cascades, we expect a rainless summer. The surprise comes that rare rainy year when the soil stays moist and we gather bucketfuls of chanterelle mushrooms in early October. Though the majority of maritime Northwest gardeners do not enjoy deep, open, moisture-retentive soils, all except those with the shallowest soil can increase their use of the free moisture nature provides and lengthen the time between irrigations. The next chapter discusses making the most of whatever soil depth you have. Most of our region's gardens can yield abundantly without any rain at all if only we reduce competition for available soil moisture, judiciously fertigate some vegetable species, and practice a few other water-wise tricks. Would lowering plant density as much as this book suggests equally lower the yield of the plot? Surprisingly, the amount harvested does not drop proportionately. In most cases, having a plant density 1/8 of that recommended by intensive gardening advocates will result in a yield about half as great as on closely planted raised beds. Internet readers, In the print copy of this book are color pictures of my own irrigationless garden. Looking at them about here in the book would add reality to these ideas. End of chapter 2.